This video describes concepts of fluids in motion. This topic is sometimes called fluid dynamics or hydrodynamics. Specifically, this video will address the equation of continuity and Bernoulli's principle. In order to understand the behavior of fluids, we have to make some assumptions and consider the fluid's ideal to simplify our understanding. For all of our examples, we must assume we are working with ideal fluids. Ideal fluids are non-viscous, meaning that when the fluid flows, there is no friction acting between the molecules. Think of a viscous fluid like honey, corn syrup, or molasses. These fluids flow very slowly because of friction between the molecules. We will assume all of our ideal fluids have no friction between molecules when they are flowing, and thus are non-viscous. We also must assume that fluids are incompressible. Because molecules in fluids are spaced further apart, there is room for the molecules to compress so that the liquid or gas would take up less space. Liquids can be compressed slightly, and gases can be compressed to a greater extent. We will assume these fluids are not compressible and thus do not change density. Finally, we will assume that these ideal fluids move in such a way that their motion is streamline or laminar, meaning that each molecule follows the path of the molecule in front of it with smooth motion. A fluid would flow steadily through a piece of pipe as shown in the bottom picture. In contrast, turbulent is chaotic as shown in the upper pipe. The molecules move in a circular fashion known as eddy currents. But again, we will assume that this is laminar or streamlined flow for all ideal fluids. Consider an ideal fluid flowing through a pipe which changes cross-sectional area. It starts out wider, then becomes more narrow. Consider a small bit of fluid with a certain mass. The mass of the fluid fills a volume V in the pipe and has a cross-sectional area A1. We can determine the rate at which the fluid flows through the pipe in terms of its mass. This is known as mass flow rate, delta M over delta T. However, since we don't know the mass of the bit of fluid, we can substitute density times volume in for mass. So the equation becomes rho delta V over delta T. But if we don't know the volume of the fluid, then we can substitute A times delta D, where A is the cross-sectional area of the cylinder and delta D is the width of the bit of fluid that we are considering. Notice though, when we combine distance over time, we get speed. Therefore, substituting lowercase v in for delta D over delta T, we get mass flow rate equals rho A V, or density times area times speed. But what if that fluid continues to move through the narrow section of the pipe? How does the mass flow rate into the pipe compare to the mass flow rate out of the pipe? The mass flow rate into the pipe must be equal to the mass flow rate out of the pipe. Otherwise, we would no longer have a steady flow. This follows the law of conservation of mass. If 5 kilograms of fluid flows into the pipe, then 5 kilograms must flow out. If 5 kilograms were to flow in and only 3 kilograms were to flow out, then there would be 2 kilograms accumulating within the pipe, and this defies steady flow. Also, it's impossible to have 3 kilograms flowing in and 5 kilograms flowing out. In conclusion, mass flow rate is constant, or the mass over time in is the mass over time out. So by conservation of mass, the mass flow rate in must equal the mass flow rate out. But we said that mass flow rate is equal to rho AV, or density times area times volume. So we'll plug in that equation into both sides. Notice because we're assuming an incompressible fluid, the density of the fluid does not change. So rho 1 equals rho 2. We can then cancel density out of the equation, and we're left with A1 times V1 equals A2 times V2. This is known as the equation of continuity, which states that when there's a larger area opening, the fluid moves with a lower speed. And when there's a smaller area opening, the fluid must be moving at a greater speed so that it flows steadily without accumulation or compression. You may be aware of this relationship already. When you pinch the end of a hose, creating a smaller area opening, the fluid exits the hose with a greater speed. When you have a larger area opening, the fluid exits the hose with a lower speed. Another way to measure flow rate is in terms of the volume that flows through a point in a given amount of time instead of mass. This is known as volume flow rate, or volume rate of flow. Recall that volume of a cylinder is equal to cross-sectional area times length, or in this case, distance, delta D. So substituting A delta D in for volume and combining delta D over delta T, distance over time, to make speed, we find that volume flow rate equals the cross-sectional area times speed. But as the equation of continuity states, A times V is a constant, which means that the volume flow rate is constant as well. Or delta V1 over delta T1 equals delta V2 over delta T2. This is the same statement as A1 V1 equals A2 V2, the equation of continuity. This again supports the assumptions that the fluid is undergoing steady motion without accumulation and also without compression or change in volume. Let's try a problem using equation of continuity. A shower head is connected to a water hose with an inner diameter of 1 centimeter. The shower head consists of 40 holes, each 0.1 centimeters in diameter. Water flows at a speed of 1.6 meters per second through the hose, leading to the shower head. At what speed does the water come out of the shower head? Pause the video time to work on the solution. The equation of continuity states that A1 V1 equals A2 V2. Because these are round pipes, the cross-sectional area is pi r squared. So we can expand the formula for equation of continuity to state pi r1 squared times V1 equals pi r2 squared times V2. We will assign 1 to be inside the pipe and 2 to be the holes of the shower head. So for radius of the pipe, we plug in 0.005 meters because the diameter is 1 centimeter, meaning radius is 0.5 centimeters, and converting to meters, we divide by 100. So we get 0.005 meters. Also, speed in the pipe is 1.6 meters per second. On the right side of the equation, for the shower head, the diameter of each hole is 0.1 centimeter, so the radius of each hole is 0.05 centimeters. Then converting to meters, we divide by 100 to get 0.005 meters. But because there are 40 holes, we have to multiply the area of one hole by 40 to get the total area of all the holes together. Solving for the speed, we get 4 meters per second. This means that because the speed is high leaving the shower head holes, the total area of the shower head holes must actually be lower than the total area of the pipe. Let's try another problem using volume flow rate. Water comes out of a faucet with a 2 centimeter inner diameter opening at a speed of 3 meters per second. How long does it take to fill a 0.6 meter by 1.5 meter by 0.0 meter bathtub? Pause the video for time to work on the solution. Volume flow rate equals area times speed. The area of the circular faucet is pi r squared. The volume that must flow out of the faucet is equal to the volume of the bathtub because the bathtub is filling. Volume is length times width times height. So plugging in length, width, and height of the bathtub, and then radius of the faucet, and speed coming out of the faucet, we solve for time and get 382 seconds. Swiss mathematician and physicist Daniel Bernoulli is known for his applications of mathematics to fluid mechanics in the 1700s. He stated that for an ideal fluid without viscosity, an increase in the speed of the fluid occurs simultaneously with a decrease in pressure or a decrease in the fluid's potential energy. Let's take a look at some of his findings. Assume we have a pipe that's wider on the left and narrower on the right. According to the equation of continuity, on the left, where the opening has a larger cross-sectional area, the speed of the fluid is lower. On the right, where it has a smaller cross-sectional area, the fluid must be flowing faster. So, as the fluid enters the constriction, the fluid accelerates or speeds up. According to Newton, if an object undergoes an acceleration, then there must be a net force in the direction of the acceleration. Therefore, there must be a net force on the fluid to the right. In order to have a net force to the right, there must be imbalance in the pressure on either side of the fluid. If there's a net force to the right, then the pressure acting to the right must be larger than the pressure acting to the left. So, putting it all together, where the area is large on the left, the speed is lower and the pressure is higher. Where the area is smaller on the right, the speed is greater and the pressure is lower. Let's take a look at a few demonstrations. In our first example, a hose is attached to an air compressor at one end and a funnel at the other. As we can see, the air is certainly being pushed out through the funnel. However, when a ball is placed in the funnel, we would expect the air to push the ball out of the funnel, but instead, the ball remains inside the funnel. Flipping the funnel upside down should do the trick, right? Again, it's clear that the air is coming from the funnel. But again, when a ball is placed in the funnel, it doesn't drop. It remains suspended in the funnel. How could this be? Well, this is Bernoulli's principle. As the air enters the funnel, it travels through a small area, meaning it must be moving at a higher speed, and thus has a lower pressure. However, as the air continues through the funnel, which widens, the area becomes larger, causing the speed to decrease and the pressure to increase. This means toward the top of the funnel there's a higher pressure and near the bottom of the funnel a lower pressure. Because there's imbalance in pressure, there's a net downward force on the ball, keeping it in the funnel. The same is true when the funnel is upside down, but the imbalance in pressures actually creates a net upward force to counteract the effects of gravity. The only way the ball would fall is if the weight of the ball was higher than the net upward force caused by the fluid, or if the fluid was to stop. The equation for Bernoulli's principle can be derived from the setup shown above. We will study the changes in the fluid as a result of moving through a pipe that changes both height and cross-sectional area. We will consider a small amount of this fluid with a mass m as shown in the diagram. The mass of the fluid m in the upper picture causes the fluid to move through the pipe, and amount m shown in the lower picture. A few things we should notice about the picture: the height is changing from position y1 to a position y2 above some reference level. Also, the fluid shown in the upper picture has a width delta L1, or moves a distance delta L1, which then results in the fluid moving as shown in the lower picture, where the fluid has a width delta L2, or moves a distance delta L2. Notice delta L2 is actually thinner than delta L1 because the pipe is wider in the second picture than in the first picture. Also notice, because of the change in cross-sectional area of the pipe, the fluid will change speed. Where the pipe is more narrow, the speed V1 is higher, and where the pipe is wider, the speed V2 is lower, as a result of the action of continuity. Finally, it's important to note the forces that are acting on the fluid. At position 1, we can see that the fluid noted as M has a net force to the right acting on it as a result of the fluid behind it. Force is equal to pressure times area, so we say the force on the fluid at position 1 is pressure 1 times area 1. Now, notice at position 2, where the speed is decreasing, the net force acts on the fluid to the left, as the direction of acceleration is to the left. The fluid is slowing as it enters the more wide section of the pipe. Here, in the second position, we say that the force at position 2 is equal to P2 times A2 and is directed to the left. Let's now combine all of these changes into one relationship. From the work-energy relationship, we know that the work done by non-conservative forces equals a change in mechanical energy. Remember, if there's no work done by non-conservative forces like friction, then there is no change in mechanical energy. But in this case, there are non-conservative forces, so we have to take those into account. Using this relationship, let's calculate the work done on the fluid at positions 1 and 2. We know that work is equal to force times distance. So work 1 equals F1 times delta L1, the distance the fluid moves. But as we said in the last slide, force equals pressure times area. So work 1 is equal to pressure 1 times area 1 times delta L1. Remember, it's positive because the fluid behind it applies a force in the direction of motion of the fluid. At position 2, the work done equals times distance, but the force is directed toward the left because the fluid in front of it applies a force to the left on the fluid behind it to slow it down. So, work is equal to negative F2 delta L2. But again, force equals pressure times area, so work 2 equals negative P2 A2 delta L2. Well, total work is work 1 plus work 2, so we plug in work 1 and work 2 into the left side of the equation and change delta L, or delta ME, to ME2 minus ME1. We also know the mechanical energy is kinetic plus potential energy, so we plug in the equations for each, 1/2 mv squared for kinetic energy and mgh for potential energy. We can then rearrange the equation so that all the 1 terms are on one side and all the 2 terms are on the other side. Now, volume equals area times delta L, so we can divide each term in the equation by the volume, written as A delta L. And then, because mass divided by volume is density, we can eliminate mass divided by volume and replace it with density rho. Thus we find that P1 plus 1/2 rho V1 squared plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH2. Or, in other terms, P plus 1/2 rho V squared plus rho GH is a constant. It doesn't change, same all the time or in any position. Both of these expressions are known as Bernoulli's principle, which essentially is a statement of conservation of energy. Let's try a problem involving Bernoulli's principle. A water tower is 6 meters above the ground. Find the speed of the water coming out of the faucet at ground level. Pause the video for time to work on the solution. We'll begin with the expression for Bernoulli's principle. We will call position 1 the water tower, and position 2 will be the faucet. Because both the faucet and water tank are exposed to the same atmospheric pressure, we can cancel the P1 and P2 out of the equation. Even if the water tank is completely closed, atmospheric pressure still acts on the water inside the tank. Also, we can say that the water in the tank is essentially motionless. Even though the water level will be dropping, this takes place rather slowly, so we can say V1 is 0, meaning that the 1/2 rho V1 squared term is 0, and we can get rid of it. Also, the faucet is considered the lowest point of the fluid's motion, so we can say height 2 equals 0, and therefore rho GH2 is 0, so we can get rid of it as well. We are left with rho GH1 equals 1/2 rho V1 squared. But because the density of the water is unchanged, assuming an incompressible fluid, then we can cancel the densities. Plugging in G as 9.8 meters per second squared, height is 6 meters, we can then rearrange to solve for speed, and the speed of the water leaving the faucet turns out to be 10.8 meters per second. Practice problem number 4. A wind gust of 15 meters per second blows across a 0.8 meter by 1.5 meter window. A. Estimate the force produced by pressure difference on this closed window, and B. What's the direction of this force? We will assume that the density of air is 1.29 kilograms per meter cubed. Pause the video for time to work on the solution. First, we are looking for the difference in pressure inside and outside the window, so we'll start with Bernoulli's principle since we have fluids in motion. Inside the house, air is essentially motionless, so we can say V1 equals 0. And we'll get rid of the 1/2 rho V1 squared term. The height of the fluid on either side of the window is the same, so we can cancel the rho GH terms out of the equation. Plugging in density of air and the speed of the air outside, we see we have two unknowns, P1 and P2. However, this is not a problem because we aren't looking for each pressure inside and out, we're trying to find the difference in pressure. So we subtract P2 from both sides, and now on the left side of our equation we have P1 minus P2, which is the difference in pressure. So we calculate the difference in pressure to be 145 pascals. Now we're asked to determine the force on the window. Well, force is equal to pressure times area, and in this case, we'll use pressure difference. So, multiplying 145 pascals by the area, which is length times width of the window, we determine the force to be 174 newtons. Because there's a lower pressure outside the window, where the speed of the air is high, and a higher pressure inside the window because the speed of the air is low, or essentially 0, then there must be a net pressure outward and thus a net force outward. Problem number 5. On the afternoon of October 29th, 2012, Hurricane Sandy had sustained winds of 90 miles per hour, which is about 40 meters per second. Estimate the pressure at the center of Sandy at that time. And we'll say the density of air is 1.29 kilograms per meter cubed, and atmospheric pressure, recall, is 10 to the 5th pascals. Pause the video if you need time to work on the solution. We begin with our expression of Bernoulli's principle. The height of the fluid in each case is the same, so we can cancel rho GH terms out of the equation. We will also say that outside the hurricane, the wind speed is essentially 0, so we can get rid of the 1/2 rho V2 squared term. We plug in the density of air as 1.29 kilograms per meter cubed, and the speed of air inside is 40 meters per second. The pressure outside the hurricane is atmospheric pressure, or 10 to the 5th pascals. And solving for P1, the pressure inside the hurricane, we get 98,968 pascals. In reality, the pressure data reported by weather centers for Hurricane Sandy was 94,300 pascals. Why do you think the actual pressures measured were less than the theoretical pressure that we just calculated? Remember, we are assuming that the air acts as an ideal fluid, which is incompressible and moves with no internal friction. We know this is not how real fluids behave, so this explains why the actual pressure was lower than our calculated value. An interesting practical example of Bernoulli's principle is the lift force that acts on an airplane wing. Airplane wings have a particular shape, which we will call an airfoil. When air, or another fluid, moves past the airfoil, we see that the fluid above the wing has to curve, and thus travel a farther distance than the fluid below the wing, which takes a nearly straight path. Assuming steady, streamlined flow, the molecules above and below the wing have to move past the wing at the same time. Because the molecules above the airfoil travel a larger distance in the same amount of time, they must be traveling faster than the molecules below the wing. As a result of Bernoulli's principle, where the air moves faster, the pressure is lower, and where the air moves slower, the pressure is larger. Because there's an imbalance in the pressures, there is an imbalance in the forces. The force beneath the wing is greater than the force above the wing, resulting in a net force upward, which we call the lift force. Let's try an example to highlight the use of Bernoulli's principle for airplane wings. A jet has a total wing area of 525 meters squared. This includes the area of both wings. If the effective air speed is 290 meters per second above the wings and 240 meters per second below the wings, what is the lift force on the jet? And for our example, we'll assume the density of air is 0.366 kilograms per meter cubed at this 11,000 meter altitude. Pause the video for time to work through the solution. We'll begin with Bernoulli's principle since we are working with fluids in motion. We can cancel the rho GH terms out of our equation because the height difference between the top and bottom of the wing is negative. Plugging in density of air at the altitude of 11,000 meters and the speed of air above the wing, then density of air and the speed below the wing, we see that there are two unknowns. But here we are not concerned with the individual pressures above and below the wing, but instead the difference in pressure. So we bring the pressures to the same side and all the other terms to the other side, and we will calculate the pressure difference to be negative 4,850 pascals. It is fine that we get a negative pressure difference because we only want the magnitude anyway. To determine the force provided by lift, we must multiply pressure difference by area of the wings, and we find the force to be 2.546 times 10 to the 6 newtons. This is an upward direction because the pressure below the wing is greater than the pressure above the wing due to the differences in speed. Problem number 6. We'll use the picture to the left. There's a pump at the lowest point, and the pump has a diameter of 2.5 centimeters. The pump sits 22 meters below a bend in the pipe. The upper section of pipe is 1 meter long and has a diameter of 0.7 centimeters. And then we have a faucet opening at the top, which has a diameter of 1 centimeter. Water is to come out of the faucet at 2 meters per second. A, how much gauge pressure should the pump provide? And B, what's the gauge pressure before the water leaves the faucet? We'll call position 1 the pump, position 2 the upper pipe, and position 3 the faucet opening. Pause the video for time to work through the solution. Part A asks us for the gauge pressure required in the pump. Because we're dealing with fluids in motion, we'll start with Bernoulli's principle for the pump and the faucet, points 1 and 3. At the pump, which is the lowest point, the absolute pressure is atmospheric pressure plus gauge pressure. At the faucet, P3 is just atmospheric pressure. We can also plug in our other values. We have the density of water, 1,000 kilograms per meter cubed. We don't know the speed, V1. The speed at the faucet is 2 meters per second, and the faucet is at a height of 23 meters above the pump, the original 22 meters plus that extra 1 meter above the pump. The problem is, we don't know the gauge pressure or the speed that the water leaves the pump, so we have to find the speed coming out of the pump using the equation of continuity. According to the equation of continuity, A times V is a constant, meaning that A1V1 equals A2V2, which is also equal to A3V3. We can plug in pi r squared for the area, the cross-sectional area of the pipe, and we'll plug in each radius and solve for the speeds. And we find that V1 equals 0.32 meters per second, and V2 equals 4.08 meters per second. But we're not yet concerned with V2. We're still looking at positions 1 and 3. So V1 is the important piece here, 0.32 meters per second. So now we can take V1 and plug it into our upper equation for Bernoulli's principle. And now we only have one unknown because we know atmospheric pressure is 10 to the 5th pascals. Our only unknown is gauge pressure. And solving for gauge pressure, we get 231,950 pascals. Part B asks us to find the gauge pressure before the water leaves the faucet. So we'll assume that the water is still at position 2 in the pipe, but we'll say that it's at the height at which the faucet is located. So the h's are the same, and therefore we can cancel the rho gh terms out of the equation. Within the pipe, absolute pressure, P2, equals atmospheric plus gauge pressure. The density of water is 1,000 kilograms per meter cubed, and we have the speed at position 2 and position 3, so we can plug those in as well. Because atmospheric pressure is present on either side of the equation, we can cancel it out. Then rearranging to solve for gauge pressure, we get negative 6,323 pascals. All this means is that the absolute pressure is below atmospheric pressure. We can conclude with a few more practical examples of Bernoulli's principle. Perfume atomizers use Bernoulli's principle. When the bulb is squeezed, air is forced out of the bulb and through the horizontal tube at a high speed. Because air moves through the horizontal tube at a high speed, the pressure becomes lower in the horizontal tube. But because the perfume in the container is essentially at rest, the pressure is high within the container. The perfume is then forced from an area of high pressure to an area of low pressure and gets pushed up into the vertical tube and out of the atomizer. The reason a baseball can be thrown with a curve is also based on Bernoulli's principle. As a ball moves through the air, we can see the streamlined paths of air molecules moving past the baseball. In order to curve the ball must be held and thrown in a certain way such that spin is given to the ball. If the baseball is spun in a counterclockwise fashion, as shown in the diagram, which represents a top-down view of the ball, the top of the ball moves in a direction with the air molecules, causing the air to actually move slightly faster, resulting in a lower pressure. The bottom of the ball rotates against the direction of the air molecules, causing the air molecules to move slower and results in a higher pressure. Objects move from higher pressure to lower pressure, so the ball will actually move toward point B and away from point A. Remember, because this is a top-down view, the ball will actually curve to the left, and as you can probably conclude, spinning the ball in a clockwise fashion will cause the ball to curve to the right. In addition, a sailboat uses Bernoulli's principle because air moves past the sail, and based on the tilt and curve of the sail, the air applies pressure on the sail, causing the boat to move in a certain way. As shown in the picture, air moves faster across the curved front of the sail and slower across the back side of the sail. This produces lower pressure on the front of the sail and higher pressure on the back of the sail. This in turn produces a net pressure and a net force. Because the keel of the sailboat opposes the horizontal component of the net force, this results in a net force forward direction. So even though the wind is a headwind coming and hitting the front of the boat, the sailboat can still move forward against the wind, as long as the sail is tilted the right way. One final application of Bernoulli's principle is known as Torricelli's theorem. Consider a container filled with a fluid, and the container is open to atmospheric pressure at the top. The container has 3 holes in the side at different heights or depths. We will start by calling position 1 inside the container, and position 2 will be each of the individual holes on the side of the container. Because we're dealing with fluids in motion, we can apply Bernoulli's principle. Because both the top of the container and the openings, or holes, are open to the atmosphere, the pressures are the same, so we can cancel them out of the equation. We will also say that the fluid in the container is essentially at rest, so we can cancel the 1 rho v1 squared term. In addition, we can say that the hole represents the lowest point that the fluid could reach within the container, so the height is 0 and therefore we can cancel the rho GH2 term. Thus, we are left with rho GH1 equals 1/2 rho V2 squared. Remember, though, that rho GH is gauge pressure, which is pressure at a depth. This means a greater depth beneath the surface, or a greater gauge pressure, means that the fluid travels at a greater speed when exiting the opening. So, as shown in the diagram, the top hole is not very deep within the fluid, or deep beneath the surface. So because the depth is small, the gauge pressure is small, and the speed exiting is small. The middle hole is at a greater depth beneath the surface, so the gauge pressure is higher, resulting in a higher speed when the fluid exits the opening. And finally, the bottom hole has the greatest depth and the greatest gauge pressure, so the speed coming out of the opening is the greatest at the bottom. We can then further apply this to projectile motion, and we see that the bottom hole has the greatest speed, so even though it's not very high off the ground, the fluid actually goes further. In contrast, the upper hole has the lowest speed, so the fluid doesn't go as far.